Hello all, I welcome you all to the fourth lecture in this course EE698M. The last time we met, we spoke about the origin of quantum mechanics, and then we did some linear algebra, right? We spoke about vector spaces and and operators and such. So we will kind of backtrack our own steps. We will see those things once again in this lecture and then take one step further. Okay, so these are some crucial aspects of quantum mechanics, so I'm spending a little bit more time on these aspects once again. If there are some repetitions, uh, it is pre-planned. Okay, it's by intent. Okay, so let's go back. Okay, so previously we saw, let's take a look again at a vector in three-dimensional space. Okay, so something like this. Let's assume we have some vector here. Okay, this is along x direction, y direction and z direction, and let's say its intercept along x is x prime, along y is y prime, along z is z prime, right? And let's say this vector is a vector, so we can write a vector as its coordinates, right? X prime, y prime, z prime. This is the typical way we have been writing, or you can also write it in this format: x prime, y prime, z prime, right? So these are the two ways to write a vector in three-dimensional space. And let's think about it. Instead of this three-dimensional space, quite in the lines of Interstellar or some movie of that sort, let's assume an n-dimensional space. Okay, so if a vector lies in n-dimensional space, you will very soon see that it does not have to be all fictional. It may seem like abstract right now, but even this n-dimensional space as its use, we'll very soon see why this is necessarily true. Okay, so in n-dimensional space, this a vector can be written as, again, in these two fashions. So instead of x, y, z, we will run out of alphabet, so I'm going to write x1, x2, so on till xn, being n dimensional, right? The same thing you can write in the other form, x1, so on till xn, right? So in this, these numbers, okay, so x1, x2, x3, they are all intercepts along n normal vectors, right? So basically, to represent a n dimensional vector, you need the intercepts along n orthonormal axis, right? So this is what we have conventionally followed, but there is a mathematical basis behind this. Okay, so let's very quickly see this. I'm sure you must have seen this in your courses in linear algebra, but I will just revisit it very quickly so that we are all in the same page. For a person who have not taken linear algebra courses in their undergrads or early masters, so this will be a useful thing. Okay, so in a normal three-dimensional world, you represent only three indices, right? Because there can only be, in this normal 3D world, right, there can only be three mutually normal vectors. So I'm just going to write it, right, because this is an important thing. In our 3D world, you can at most find three mutually normal vectors. So I am already using normal because we have previously defined our inner product space. So if two vectors a and b are said to be normal, if their inner product as defined by this turns out to be 0. And this is not only true for this 3-dimensional space, it is true for any n-dimensional space, because we have defined this as such, right? We can go back to our definition of inner product and then you will see this is true, right? But in a normal 3D world, you can at most find only 3 mutual normal vectors, and any fourth vector that you consider in this 3D space will be along the lines of any one of them, right? Or you can always represent, another way to say this is, you can always represent any vector in the 3D space. I'm going to write this again. You can represent any vector in 3D space as a linear combination of 3 orthonormal vectors. And this is something that we take for granted, right? So when we write our normal a vector in 3D space, we just mention 3 intercepts along 3 axes. So these axes are actually vectors which are orthonormal to each other, right? So that is the origin of this. So you take one along x to be, like, say, I vector, j vector, and k vector, right? So you write A as x prime I, y prime j, z prime k, because these are the intercepts along those directions. And you can go about to prove that the inner product space is a projection of a one vector over the other, but we are not going there because for the lack of time. Okay, so the collection of mutually orthonormal vectors, so in a 3D space it is along the 3 axes, but in an n-dimensional space you can again find, okay, so this is 3, right? So you can extend this to n-dimensional space. You can at most find n orthonormal vectors. We can, this orthonormal vector is just a subset of vectors which are linearly independent, right? So again, this is pure linear algebra, so we don't have to go there, but orthonormality indicates that you have n linearly independent vectors, in the sense that you cannot represent any one of these. Okay, so let me write it again. So let's say the set of such orthonormals vectors is called as a basis. So let us see, this B is a set that I define x1, x2, so on till xn, and these xn's are vectors, and these xn's are orthonormals as I have defined here. For a 3-dimensional space, this is just x1, x2, x3. These are 3 normal vectors. For n-dimensional space, you should find n. You cannot, any xn plus 1 will not be perpendicular to all the numbers. So basically here what we mean is, for any I comma j belonging to 1 to n, xi, xj is 0. So this is the definition, right? So these are all orthonormal, but it does not have to be orthonormal. It just have to be linearly independent, in the sense that you cannot write x1 as a linear combination of other vectors, right? So x1 cannot be represented by any linear combination of any other vectors, and for any n-dimensional space you will have n linearly independent vectors. Orthonormals are just an example of linearly independent vectors, so we will drop this discussion at that. Okay, so this B, this is called a basis set, and these vectors are called as basis vectors. Okay, so, and let's say I'm going to okay, so this is normal linear algebra. Okay, in quantum mechanics, now let's go to Now let's go to specifics in the case of quantum mechanics. A vector which we wrote as like this in the normal convention, in quantum mechanics it is written in this particular fashion. This is called as a ket. It's also called as Dirac notations. Okay, so we write a ket like this, which is once again a set of numbers. Okay, a1, a2, so on till an, depending upon the dimension of this system, right? And similarly, let's say we have another vector b written in this particular fashion, b1, b2, so on till bn. If both of them live in the same space, they should have the same number of components. This n should be the same, right? So let's assume that both of them live in the same space, and that's the Hilbert space. Last time we saw that the space in which they are all square integratable, it's called as the Hilbert space. So these are all living in the Hilbert space. Okay, and if b vector is normal to a vector, right, and we saw this inner product b, it is written in quantum mechanical language as this. You will see the reason why, because the way the inner product we previously defined, it is this, right? b1 star a1 plus b2 star a2 plus so on till bn star an, right? And if it is normal, this should be 0. So this is 0. And in any conventional case, if a and b are not normal, this inner product is generally a complex number. And is 0 if a and b are normal, right? And if we write a and b are the same, it will always turn out to be that a1 star a1 plus a2 star a2 plus so on till an star an. And you can clearly see that even if a1 and a1s and all these things are complex, the a1 star a1 is going to be a real number. So this number is always going to be real, and it is always, if it is 1, it is called as, the vector is called as normalized vector, right? And if this value is lesser than infinity, then the vector lies in the Hilbert space. This is what we saw, right? This is called square integratable, and so this is basically mod square, right? So if a vector is square integratable, then it lives in the Hilbert space, right? So now we are already in the n-dimensional space, right? We have come away from the 3-dimensional space. We are already in the n-dimensional space. Now let us take a look at this A, which we represented as in this big matrix, right? So which is a1, a2, a3, so on till an. I can actually plot it. Small a's, I am plotting it against the indices 1 to 2, so on till n. There are n indices, right? And let's assume if it looks something like this: 0, 1, 2, 3. This is 1, 2, 3, 4. Again 0, and continuously 0 from there on, right? If it is something like this, of course a1 is going to be 0, a2 is 1, a3 is 2, a4 is 3, 4. Again it comes back 3, 2, 1, 0, so on, right? So you can see that if this n is a very large number, these points get too close or close enough such that it starts to look like a continuous function, right? So if n is incredibly large, a very large dimension number, then this discrete points can be converted into a continuous function, and hence this a, which was once a vector, is also equivalent to a function in the limit n tends to infinity, to a very large number. So whatever the discrete vector that we said in the n-dimensional space can also be converted to an infinite dimensional space. So this n we have already converted to an infinite dimensional space where it is just a function. So we have transformed something from a three-dimensional space to a n-dimensional vector space to an infinite dimensional function, right? So this is the motivation to actually jump from a three-dimensional space to a larger dimensional space. And when we meet with functions, now things become much easier for us to handle, because the inner product of an infinite dimensional space, let's say this b direct a, if both b and a are an infinite dimensional vectors are now functions, we can write the inner product as like this. Oops. Okay, b star a. Remember, both of them are functions of x, and this x is an along this, right? So x is x1, x2, x3 all the way to infinity. So if this is small enough, we can consider dx something in this, right? So here I have something for you as a homework. If a and b are infinite dimensional vectors living in Hilbert space, can you prove that the inner product space is always lesser than infinity? So that means that inner product space, inner product always exists. So it's called as an inner product space as well. But again, here we assume this. So previously we talked about vectors living in Hilbert space. Now we're talking about functions because it's n tending to infinity, right? So again, we can define a few things. If there exists functions f1 so on till fn, and they are orthonormal. So what I mean by orthonormal is fj, fi, fj is equal to 0 if I not equal to j, and if fi, fj equal to 1 if I equal to j. Okay, they are also normalized. And if such functions, if the set of such functions are complete, what I mean by are complete is any function g of x can be represented as a summation n tending to 1 to infinity cn fn of x. So these fn's are orthonormal functions. That's what we have defined, and you have some n which is infinitely large, right? That set of orthonormal functions are said to be complete if you can write something like this. Any other function g of x can be written as a linear summation of such functions. Remember, this is very reminiscent of your Fourier, right? So these fn's are your sinusoidal functions, and this cn, the coefficient, can easily be written as a linear product of, inner product of fn and g. So this is once again a hangover from our Fourier series representation, right? So any of these coefficients Cn can be obtained by the inner product of g, the function that you want to find, and its inner product with the basis functions that we already know, right? So here there is a pitfall which I'm just mentioning here, and we will not go because it is beyond the scope of our work, right? So we told that if you have a vector which is n dimensional vector space, right? So you will have n linearly independent vectors, right? Now if we take a function which is an infinite dimensional space, what is the number of functions that you can find which are linearly independent, right? So that means that you have an infinite number of functions which can be linearly independent, and hence this summation should again be an infinite summation, right? So when we work with infinite summations, it's really hard for us to come up to a solution. So we use what is called as Dirac approximation. So what Dirac assumed is any of the functions in which the quantum mechanics deals with, right, it is always such that the C ends as n tending to infinity goes to 0, right? So basically what happens, you can have a n dimensional space, but any of these contributions of the nth dimension or infinite dimension functions to the actual function that we care is normally 0. So this is to tell that if you have a function something like this, right, as x tending to infinity, it always comes down to 0, because it is only those functions that we can work with, because it's easy, because it is these functions that we can prove are actually square integrative, right? So let's now that we are working with infinite dimensional spaces, we can define an operator as we did in our previous lecture. An operator P acting on an vector or a function A which is infinite dimensional transforms this function to another function B, again to an infinite dimensional space, right, where A and B are once again infinite dimensional functions as we saw previously, right? And if acting on A gives A back, we call this as an Eigen equation, and A as the Eigen function of operator P with an eigenvalue lambda I. So this is a direct relation between the finite dimensional spaces to an infinite dimensional space. And if in this definition A P vector A is equal to P vector A, right? If there exists a P such that this relation holds true, then this P vector is called as Hermitian, and for any two vectors, or we are talking about functions here, any two functions f and g, if such a relation is true, okay, if there exists a Hermitian operator P, then we can take any two functions and also prove this to be true. once again these brackets are inner product spaces as we saw previously. We can move this P here and there, right? This is just to prove that P equal to P star, right? So this is the definition of an Hermitian operator. This is true only if this can be true. Okay, so and we also know that any eigenvalue of P will be real and all those things, right? So P acting on A, if you get lambda A, then lambda A is real if P is Hermitian. In quantum mechanics, we define what is called as an expectation value of an operator. So it is typically written as like this. Okay, an expectation value is defined something like this. Let's take any function f. Yes, so dx, or it is an inner product of f pf. Okay, and this number, because P is an Hermitian, this number is always real. This can also be trivially proved. This will be a part of your homework, right? If P is an Hermitian operator, expectation of a Hermitian operator is always real, right? So expectation value is something that you typically measure experimentally, and hence a Hermitian operator in quantum mechanics is typically called an observable. So you don't have to really worry about these terms right now, but all we would like you to carry forward is, if there exists an operator P, okay, whose expectation, which is an Hermitian, if the operator is Hermitian, then the eigenvalue of this Hermitian operator is going to be always real. The expectation value of this operator is always going to be real, and the operator is always is called in quantum mechanics as an observable. Okay, so now let us take an example of this and then study these operators a little bit more in detail, right? So let us assume an operator, something of this sort, h cross by I d by dx. So this is an operator, right? Now, is this operator linear? So what's the meaning of a linear operator? So P acting on lambda A, if it gives lambda P acting on A and P acting on A plus B gives P acting on A plus P acting on B. So if we define P like this, it is clearly that P is going to be a linear, because both these are going to be true, and hence this definition of P is going to be, so P is a linear operator. Okay, so here I'm already using H cross. H bar is called a reduced Planck's constant. Of course, you might have known this before, and I is the complex. I is equal to root minus 1. Okay, so this H by I is a constant. So I use this because this is going to be useful later on in our discussion, but for all our current discussion, it can be a constant. You can call it C. It does not really matter. I just define it in this way because eventually we will use P in many places, and in that this constant has to appear in this particular form. But if we have an operator which is defined like this, now let us see let us look if this is Hermitian. Okay, how do we find if this is Hermitian? I'm going to operate on two different functions, f and g. Okay, f and g being functions as we discussed previously. And how do we define this inner product space? Minus infinity to infinity f star h bar by I d by dx g fx dx. Right? So this is how I expand this, and of course h by I can be taken out, and this integration I integrated by parts. So you get uv, which is f star g, which from minus infinity to infinity, plus or minus v du, integral minus infinity to infinity h bar by I dou f by df by dx star g dx, right? And we previously defined that if f and g belong to an inner product space, belong to an Hilbert space, then f and g at infinity and minus infinity should go to 0, right? So that's what we defined here. All these coefficients, all these cn's should go to 0. If all the cn's go to 0, any of these functions will go to 0 at infinity, right? So f and g's independently go to 0, then their product will also go to 0. So the first term will automatically go to 0, right? So all that will be left will be h cross by I integral minus infinity to infinity dou f by df by dx star g dx, and which is easily understandably is at f g, right? So I have started with inner product of f acting on g, and I have proved that this is to be true. And if this relation is true, we can tell that p, which was defined as h cross by I d by dx, is Hermitian, right? And if this is Hermitian, we can always tell that all the expectation values of p is going to be real, and p acting on any vector will give you lambda f, and lambda f is going to be real, and p is called as an observable in quantum mechanics, right? So in similar lines, remember we used p in our previous derivation as well. There is a particular reason why this is important. Of course you all might know what it is going to be, but this is how it was developed. Okay, another operator x, which is just x, can also be shown to be Hermitian, can also be shown to have all these properties. Okay, so now let's once again take a look at, so this is there is, okay, fine, let's proceed further. Okay, so let fp be an eigen function of p. There are many functions in this Hilbert space, right, out of which I'm just taking only one function fp, which is an eigen function of p. So what it means is p acting on fp gives me lambda p. Instead of lambda p, so this is like this, small p fp, right? And we know this p is real, correct? So let me write this: h cross by I d by dx of fp is p into fp, correct? So what's the general solution of fp? So if fp is a function, right, so general solution of fp for this differential equation is going to be a e power I px by h bar, right? So this is the first order equation, and we know the general solution to be something of this sort. So for this operator p defined in this particular fashion, the eigenfunctions are a family of functions with p being p being anywhere on the real line. You can have infinite number of functions which are eigenfunctions of this, each of them having p, and you can have infinite number of p's, all of them lying on the real line, right? So if we take two such functions, fp and fp dash, two such functions, okay, of eigenfunctions of p, and we want to calculate what is the inner product of this, where fp and fp dash are eigenfunctions of p. What's the inner product of this? A star integral minus infinity to infinity e power minus ipx by h bar e power ip dash x by h bar dx, right? And this is e power I p minus p dash x by h bar, right? So this will be a square 2 pi delta p minus p dash. So you know that this is the definition of infinite integrals of an exponential, right? So this will turn out to be something like this. So if we choose a square to be equal to 1 by 2 pi h bar, then the set of functions fp, right, infinite set of functions are orthonormal, in the sense fp fp1 p2 is basically, a is chosen to be like this, right? Delta of p1 minus p2, and this will be 1 if p1 equal to p2 and 0 otherwise. So basically this means that the set of functions which are eigenfunctions of an operator, they are all orthogonal. The set of eigenfunctions of p, not any operator by the way, because we chose an operator of this sort, the eigenfunctions of p are orthonormal. Okay, and of course these are all waves, right? So basically e power I k is obviously a wave, and p's, what's the, let's say, p operator acting on, let us say, p operator acting on an fp. This is h bar by I d by dx a e power ipx by h bar. Will give me p's, right? p, and the spatial wave vector k, because this is a wave, right, and you know what is the spatial wave vector of k, is p by h bar, or it is typically written as p is equal to h bar k. Okay, k is called the wave vector for any wave which is defined in this format. This is the relation, and the wavelength lambda is 2 pi h bar by k. It is just 2 pi by k, right? H bar by p. And we have once again received the de Broglie's relation. If we take the wave function, if we take the momentum operator, so this is called as a momentum operator because you can see that the Eigen functions are an infinite set of, it's an infinite orthonormal set, and the Eigen values p follow what is the relationship as described by de Broglie. This is de Broglie, and this p reminds us of the momentum as we described previously, and hence this vector as we defined here is called as the momentum vector. So this p is called as the momentum operator because the Eigen functions acting on a plane wave gives you what is called as the momentum as described by de Broglie. Right? So now let us look at the another operator, x cap is equal to x. Right? Now say gy of x are Eigen functions. Of x hat. So this is once again following how we did what we did for the position, right? For the momentum. So now we are talking about the position. So x hat acting on gy will give me y gy, right? Y being the eigenvalue, and obviously x hat acting on gy is x acting on gy is equal to y acting on gy, right? So x is equal to x. This is the original definition of the operator, right? And this can be true only if x equal to y, or x is equal to y equal to 0, right? So gy, that is the only solution for this, is a delta of x minus y. Right? Only if gy is a delta of x minus y, this relation can be true, and hence for an operator defined like this, your bunch of vectors which are Eigen functions of this operator are delta functions, right? And once again, how do we find a? We normalize, assume y is some other, okay, gy. I think maybe this y can be a little bit confusing, but let me tell you what I mean by this y. Okay, maybe I should just use x prime. Okay, so this is x. I'm saying at any point here you take it as y. Okay, so gy is any such function, and if I define an operator x, the only value which you will have a delta function at this x value. Okay, that's what we are trying to make here. Okay, so this will be given by minus infinity to infinity gy star x gy of x dx, and gy is defined in this particular way. So a square minus infinity to infinity delta star is the same, x minus y dash into delta x minus y dx, which will turn out to be double delta, right? So minus infinity. This entire function will be true only when, sorry, this will be true only when you have y equal to y dash, right? Multiplication of two deltas, it will be non-zero only when both of them are 1, and both of them can be 1 only when x is equal to, when y is equal to y dash, right? And to normalize this, if we have a equal to 1, then gy's are normalized as well as orthonormals. So if we let's recap. So we defined our momentum operator as h cross by I d by dx, and we found the Eigen Functions fp as a e power ip x by h bar, right? Like sinusoids. And we defined the position operator like x, and we find the position eigenvectors to be deltas, right? And obviously we can see this, these deltas are orthonormal. Similarly, the sinusoids are orthonormals. And given these two operators, once again we can do our previously well studied the operation of both the operators acting on a wave function. I'm writing as A is obviously not the same as P acting on A, right? Because we know that necessarily does not have to be the same. And we can define this as a commutator IH bar. So I have just now substituted x and the operator here. We can easily prove this to be equal to IH bar. So the commutator of momentum and position, in the sense that if you measure the position first and then, if you measure the momentum first and then the position on A, your result will not be the same as measuring the position first and then the momentum. This is something which is drastically different from classical mechanics, but we are still a little bit far off to actually relate this to practical circumstances. We are still talking in abstract terms where x and p are just operators. We see that the multiplication of the operator is not commutative. You cannot change things, and what is called as the commutator is the difference between the two, okay, acting on any vector will give you this. Now let us, before we proceed to our final derivation of the Schrodinger's equation, where we will stop today, I would just like to revisit our famous Heisenberg's uncertainty relation. So we will just have a small detour and then look at Heisenberg's uncertainty relation and then come back here. Okay. So now for every operator P, let's say for operator P that we saw here, we can define expectation value, which is, let's say, psi. So slowly I'm starting to use psi instead of f and a and everything that we saw previously, to tell us that we are moving closer and closer to the quantum mechanics jargon. So typical wave functions are called psi. So we start using this. So this is the expectation value. Now we can also define a variance, because these operators are now called observables. So you measure something. So when you measure, the expectation value is the mean value that you will get, right? This is what you expect. This is what you see in statistics as well. When you do your statistics, you will know if there is a probability distribution, you can find what is the expectation value, and this is what this is. And you will also have what is called as an variance. So a variance as an operator, let's say for of P operator, is defined as P minus the mean value square. So this is the typical definition. It comes from our probability theory. Okay. So now let us calculate the expectation value of a variance. So this is called as sigma t square, which is an expectation value of this operator, which is psi acting on p hat minus p square. Right? How do we calculate the expectation of this? So this is the expectation of variance. This is written as zp square. So I can go through this derivation fully, but I'll just go through a few steps and I'll give you the final result. If you're not able to get through, the math is not very hard. So what we can do is we write like this: p hat minus, because we know how this expectation comes, right? Psi p hat minus p, and of course because p is Hermitian, you can move around that, right? P is same as p star, so you can move around things. And this is an inner product of, let's say, if you write this as f, this is similar to f, and which is basically will not approximate it here. Okay. Now you can do the same thing for x. Okay, the variance of x operator is, let's say, sigma x cap, which can be written as psi x hat x operator mean value of x operator square acting on psi. Remember, psi is a wave function, right? So wave function is an it's still not an eigen function of any of these operators. Okay, it's just a wave function. Any function in the Hilbert space can be written something like this. X hat minus, right? And once again, this can be written as g, where g is defined as, okay, and f is defined as okay. So now I'm going to calculate sigma p square, sigma x square. The reason for this will become obvious. So sigma p is the variance in momentum measurement, and sigma x is the variance in x measurement. Okay, so we are just multiplying the variance in the momentum and the variance in position. I'm trying to get close to the Heisenberg's relation. Okay, so that's the reason why I multiply this, and you can clearly see that it is multiplied by g, right? And by Schwarz's inequality, we can know that this product is always smaller than the absolute value of square. So this is the Schwarz's inequality. We have seen this before. The inner product of two functions is always smaller than the actual absolute values of this product of the two, smaller than equal to. Okay, so now this is lesser than or equal to f. I have defined somewhere p hat minus average of p, x hat minus average of x. Okay, and Again, now I have to break this apart. I will get p hat x hat minus expectation value of p x hat minus expectation value of x p hat minus expectation of value of p expectation value of x. Right? Remember, this is basically, okay, I think I forgot to write this here. Thing on side. Okay, so this is lesser than or equal to mod of p hat x hat acting on psi minus x hat psi minus x hat p hat psi minus this is p hat x hat, and psi, this we have always assumed to be 1, right? So this is less than or equal to this is an expectation value of p hat x hat, right? This number minus this is expectation value of x. So this is an expectation value of x, so you got it here, minus expectation value of x, and this is expectation value of p, right? And minus this is expectation value of p, sorry, plus, it has to be plus, expectation value of x square. So this is lesser than or equal to, finally, the expectation value of px minus p. Hey guys, really sorry about a mistake. So it's not lesser than or equal to, but remember the product is always larger than, right? So this is the product of f and g is always larger than the inter product, right? So basically it has to be larger than or equal to everywhere. And here all I am trying to do is the average f bar g square, right? So let me do one thing. Let me remove this, right? So here so this is what I am trying to find here. right? Eventually what I need to find is mod. How do I find this? So I know this to be a complex number, right? So square can be written as one by 2i z minus z star square, right? So this is the mod z square. So I know z is basically f g, and z star is g star, which can be written as g f, right? And I found to be and gf can be just the opposite of this, right? Because they are the same. These are just numbers, so it does not change, right? So square is basically one minus the other, so I will get 1 by 2i right. And this precisely is 1 by 2i expectation value of p comma x. P comma x is the commutator, so the expectation of the commutator square. So the actual variance in p and the variance in x is greater than or equal to 1 by 2i, the expectation value of the operator square, right? And it can be seen that if you have two non-commuting operators, if there are two non-commuting by that I mean that the expectation value of the commutator is not equal to 0, then the variance in their measurements are related. So what I mean is, you cannot measure to arbitrary accuracy any one of the, arbitrary accuracy both the operators, both the functions simultaneously. You can measure one of them at arbitrary accuracy, then the accuracy in the other gets disturbed, because that's how this is, right? So you should have, if the variance in one operator turns out to be 0, obviously the other one blows to infinity, right? Because the other side is non-zero, right? So this is the famous Heisenberg uncertainty, which we know for p and x, but it is true for any non-commuting operators. So if you have two non-commuting operators, you will always have this relationship between the variances in their observables. Okay, so now that we have covered most of the topic, we will just end today with a very small but a crucial point. So here we will derive, or not derive, we will draw the Schrodinger's equation, and leave it at that, because the next time we come, we will talk about how do you solve the Schrodinger's equation for some known potentials. Okay, so for solving for coming up with Schrodinger's equation, we have to go back to classical physics a little bit. So we know Newton's relation of F equal to dp by dt, where p is the momentum, right? So this is one of the fundamental postulate or the definition of force. You can define force by the variation or the gradient in the momentum, which is written as d by dt of mv. This is one of the fundamental equations and cannot be derived easily. You can actually come to it from the Lorentzian action of we can come back to this equation, but then cannot fully derive it. Okay, it's a Lorentzian principle of least action, but let's not go there yet. This is called as canonical momentum. Canonical is something which is related to physical aspects, right? My measurements and such. So this is the momentum which can be measured, right? So this is something that we all know, and the work done due to this force, classically, if you have a particle in R1 and you move it to R2, the work done in doing this is integral R1 to R2 f dot dx, any small thing that is done. And if this work is independent, path independent, it does not matter if you go like this or like this, any such way, then that work can be written as the difference in potentials between R2 and R1. U is called as the potential energy. Okay, it is called a conserved force. Gravity is a conserved force, and forces like that, in which the work done by the force is independent of the path that it is taken, right? You don't have to go, yeah. And such force is written as minus del dot u, but yeah. So u is called the potential energy, and every particle has that energy if it goes from one place to the other, where the energy changes irrespective of the path that it takes. Okay, and if you have a particle which is moving with a velocity v and of mass m, we know that the kinetic energy of that particle Ek is given by half mv square. So the total energy in the Newtonian physics is At is T plus V. T is called the kinetic energy, U the potential energy. This is where the work done does not matter about the path that is taken, and T is the kinetic energy when the particle moves with a particular velocity, right? The Hamiltonian in the classical physics still, okay, H is a way to divide these two terms of the energy such that this T is only a function of P, the momentum, and V is just a function of X. X is the position, right? So if the potential energy, if you can divide the total energy with two terms, in which the first term T depends only on momentum, it's typically seen here, right? So this can be written at p square by 2m, and the potential or the potential energy can be dependent only on spatial coordinates. Then this form of writing the expression is called as the Hamiltonian, and the equation of motion for this Hamiltonian, that is how the particle's momentum changes, is minus dou h by dou x, and it is dx by dt. The position is minus dou h by dou p. These two equations can be used to completely derive the particle's momentum and the position at any time if you know the total energy h. This is slightly different from the Newtonian physics where everything is based on force, right? So force is mass into acceleration. So if you know what is the force acting on the body, you can calculate what is its position and what is its velocity at each point. You know the momentum and the position at all points. This is how Newtonian physics works. And the other way of solving classical physics is by using the Hamiltonian, where you develop the energy first, and the energy you split into two terms. The first term depends only on the momentum, the second term depends on the spatial coordinates, and you can write the equation of motion in this particular format, right? So but in quantum mechanics, obviously you know that everything is wave, right? These are all for particles, but when we come to quantum mechanics, you have to talk about waves. And let's write a typical equation for a wave. So let's say you have a wave function psi which depends upon the position and time, and I'm writing a normalized wave function because this is what stays in the Hilbert space, minus infinity to infinity psi k e power kx minus omega t. This we can come in two ways. The reasoning for why we write a wave function in this fashion. One is, this is a clear Fourier example, Fourier expansion, right? Any function in x and t can be written in this particular format. Or you can also think that e power ikx we have shown previously are momentum eigen functions, and any function phi can be written as a linear combination of the basis sets, right? So we know e power ikx are basis vectors, basis functions, and any function can be written in either way. So these are the two ways it can be written, right? So now all we know is we know the starting point, right? So let's say that we know the problem of quantum physics is, let us say that we know the wave function at time t equal to 0. Let's say it looks like this. This is psi x comma 0. The question is, what happens at time t equal to t prime, right? So does it move like this, or it moves like this? Okay, so this is what we want to see. How does the wave function progress at time progresses? So this is the question that we are talking, right? And we know the initial state. We want to see what happens at any time t. So this clearly tells us that the equation of motion for this should be first order, because we have only one initial condition. We should have only the first derivative in time, right? So d psi by dt of this particular equation that we saw here, this will turn out to be 1 by root 2 pi integral minus infinity to infinity psi k omega e power ikx minus omega t dk. Okay, so this is this expression remains the same. Just you differentiate it once, you get with respect to time, you get the omega out. And if I multiply this equation by I h bar, which will turn out to be 1 by 2 pi integral minus infinity to infinity psi k. Remember h cross omega is the actual energy, Hamiltonian, as we saw previously, right? This will turn out to be Hamiltonian e power I kx minus omega t dk. Right? So this is basically h acting on psi again. So because this omega h is, that's why we multiply this by I h cross on this side, right? So basically to give you h cross omega here, and h cross omega is the energy, right? So on the left hand side, you have what is an operator which acts on psi and gives out an eigen value of energy, right? And how do we write the operator form of h? Again, because this we know is something to give out the eigen value, and h we know now can contain two terms, t plus v, because we call this the Hamiltonian, and t is p square by 2m. This is the momentum that we saw previously, momentum operator, and v is the potential energy. This is some operator, okay? So now the equation can be written as minus I h bar dou psi by d psi, dou psi by dou t is minus h bar square by 2m, because we know what p is, right? P is h by I dou by dou x, dou square by dou x square psi of r comma t plus v of r comma t into psi, right? And in 3 dimension, obviously this del by del square turns out to be a Laplacian, and this is the famous Schrodinger equation. Right? So we started with the classical definition of energy H, right, which can be written as two terms, the kinetic energy and the potential energy. And we see that if you define a wave function in this particular format, where we know that e power ikx are momentum eigen functions, the time derivative of this will give out the energy, which is h cross omega. And the other way of deriving it is to write the Hamiltonian acting on psi. Right? The Hamiltonian is an operator which gives you energy. So we can write the Hamiltonian as p square by 2m plus v. And we expand this to give you our final Schrodinger equation. This by no means is no complete derivation, because this was indeed just suggested as a solution to a wave which can describe a particle, right? Because you came up with an energy of the particle. We know the solutions for energy of the particle, but the solution is, however, a wave, right? So if it has to follow the equations of an energy and still have a wave property, then the Schrodinger equation is one way to solve that, right? So we will stop our lectures here. The next time we come, we will see some simple examples, and we will have solutions to commonly known potentials. Thank you.